Welcome ENET 130 at Bellingham Technical College. We're continuing our study of semiconductors, and in this section we'll be discussing and introducing bipolar junction transistors. These can be thought of as basically the heart of semiconductor devices and circuits, and as an example of one of the most important things we use semiconductor devices for, and that is amplification. So we'll be introducing concepts of current and voltage gain in this section. But we're going to start out with a little discussion about what a transistor, in this context, the bipolar junction style of construction, is, how it differs from diodes, and how we can use biasing voltage external to the device to get our PN junctions in this transistor to actually make the magic and achieve the current gain that we rely on these devices to provide. So, just as an introduction, we are again, for this lecture, we'll be using the annotated version of James Fiore's textbook, and mainly drawing from his figures and my annotated notes. So, from the context of electronic technicians, when we're designing and analyzing circuits, a bipolar junction transistor can be thought of as a current gain device. We're going to apply current in a small signal to one lead of this device, and in so doing control current flowing across the main body of the device. So small signal in what we'll term the base of the device is going to control a large signal from the emitter to collector, the main pipeline. So you can think of a bipolar junction transistor as a valve. Applied at the base, it's going to control a big flow of current down the pipe from from emitter to collector. Okay, in this first lecture we're going to have several lectures that cover this in this chapter 4 in Mr. Fiore's book. But this is the first, and we're just going to focus on basically the material science of how these are made, compare them to diodes, look at our PN junctions like diodes, and then the last concept we'll introduce in this lecture is how they're not really two back-to-back diodes, and how that makes all the difference in achieving a current gain device. Okay, so we're now looking at figure 4.1. And this is a very rough and simple schematic of a bipolar junction transistor, including our external semiconductor materials. These transistors come in two flavors. Basically, we can either have two regions of N-doped material with a layer of P-doped material between them, or we can have two regions of P-doped material with an N-doped material between. So remember, in a diode we just had two regions of semiconducting material. We had an N and a P, or a P and an N, and we had a single PN junction between the two, which had a depletion zone and had fixed charge and only allowed current to flow one way. We had the energy hill that we had to overcome to get charge across it, and away we go. Well, now we have two of those. We have three pieces of semiconducting material. These are all made by diffusion. This is one big single crystal. So we dope it three different ways. In fabrication methods we're not going to discuss in this class, but be known this is not glued together or welded together. This is one monolithic piece of silicon. So it's going to follow all the rules of the materials that we studied in our first chapter. But we have a second PN junction here, and PN junctions are PN junctions. They all are the same. They work exactly the same way. They're going to transmit charge differently depending on how we bias them, what type of energy we give them in the terms of an applied voltage, so that charges can climb hills or descend them depending on the type of charge, positive or negative, electrons or holes. Most important part of this device is the base. This is the valve where we're going to put in our small signal, and in so doing we're going to control a big current signal flowing between the emitter and collector. And you'll notice in this schematic, this base middle layer, the filling of the sandwich, is thin. This is essential to the way these work. If this region were thick, it wouldn't work. In addition to being thin, it's very lightly doped. So there's not a lot of these positive majority charge carriers. There's more than in an intrinsic semiconductor, of course, but nothing compared to what you have in the collector and the emitter, especially the collector, which is very heavily doped with in this case, an N-type material that gives us lots and lots of negative electron charge carriers. There's some majority hole carriers in the P, but not too many. And when we get to the end of this lecture, we'll discuss why that's so important for making a transistor work as a current gain device. Okay, so emitter lead. So we have one type of semiconducting material, reasonably thick, reasonably heavily doped. We got our base, which is the opposite of whatever the emitter and collector are, thin, lightly doped, and the collector fairly large, very heavily doped in the same type of dopant that the emitter was. Okay, emitter, collector, base. Okay, so let's zoom in on what's going on with our PN junctions, and this should be a review from our second section where we discuss PN junctions. So this is what's going to set up in the semiconducting materials as they're fabricated. We don't need to apply any external voltages to get this. So we've diffused some pentavalent N-type dopants into this material, and we probably already had some trivalent P-type dopants in our P section. So we had already some positive charge carriers in our P region and negative charge carriers in our N region, and as you probably remember, at the interface, those recombine naturally in the material and annihilate, and so we've got a region of intrinsic semiconducting material right in here, and because we depleted some of those majority charge carriers on each side, we've got a region of fixed charge relative to the rest of the material, positive on the N side and negative on the P side. And remember, those circles mean this is an absence of the charge that should have been there, so it's reflected as the opposite. We got rid of some electrons because we combined them with holes and gobbled them up. So this area of our emitter adjacent to the depletion zone is net positive, and opposite over here. And of course, we have the same thing going on between the base and collector junction. So we have two PN junctions, just like we would in a diode, and they're basically mirror images of each other. So two depletion zones, two energy hills, pointed in opposite directions. Okay. So one of the simplest ways to think about this, which can only carry us so far, is to think about each of these depletion zones and fixed charges as a diode. Because really, if we were to cut our transistor in half, which of course we wouldn't want to do, but if we did, we'd basically have and metallize the leads on our cut interface. We would have two diodes, really, because we have a PN junction here and a PN junction there, and they're pointing in opposite directions. So that's kind of one way to start thinking about this. Again, we're not going to continue for very far because that kind of defeats the point of what makes these work. But this is one place we could start. And that's just representing the junctions. Okay, now the way a transistor works, and I'm trying to zoom in on these figures because this is where we're really going to go through it, is what's known as the biasing. We have two PN junctions, which we're representing with diodes just for the moment, but really we're looking at these regions that we just discussed up in the earlier figure. We can push charge up and down those energy hills represented by the PN junctions, and of course the way we push charge up and down a fixed voltage in our semiconductors is with an applied voltage from the outside of the device. We did that like crazy with diodes and got them to open, or we reverse biased them and kept charges from running up or down the hill as we wanted. So we can do the same thing here. PN junction is a PN junction. So let's take a look at what would happen if we put a positive oriented battery out here, and we'll just call it VEE. And that's a common type of notation that you see with amplifier circuits, and this just means this is the voltage we're applying to the emitter. And that's what that subscript double E means. And so we're gonna put the positive end. We're always going to put a current limiting resistor, Even though this is just a model, we're getting in the habit of always putting in current limiting resistors. These are heat sensitive devices. We don't want a bunch of current screaming through them. So we're getting used to good practice here, even in our schematics. So we're gonna look at pushing some conventional current, some positive charge into the device. So we're gonna try to push some positive charge this way. And as you can imagine, that's not going to work very well. Because we've got this negative doped end material. It's all going to want to migrate towards the lead, away from the junction. Junction's going to go in reverse bias, ain't going to get very far. Okay, we kind of expected that. And we can do the same thing over here on the collector. We can give it a source, and the CC means collector source, referring to the collector side of the transistor. And we can hook the base up to both and make it common. And in so doing, what we've done is very, very important. We've defined now two loops in the material. We have the base emitter loop, which we could draw. Let's see if I've got a curvy line to draw with. Here we go. I have a loop base emitter, which from the standpoint of conventional current is flowing this way, kind of a clockwise, and I have a collector base loop. And those are real. If I biased things the right way, theoretically we could get current flowing through it. Certainly isn't going to do it here because these are reverse bias. So we'll get rid of those for now. Okay, so we have two possible circuit loops. We have two PN junctions, which from the point of view of our sources right now are reverse bias. So no current's going to flow anywhere, but maybe if we turn these sources around, it certainly could. So now we have positive current trying to flow into the P material and out the N, and of course that's going to mean this is in forward bias, so check mark, current could flow, and nope, not so much there. This one's in reverse bias. So we forward biased our base emitter loop and reverse biased our collector base loop. So we could do the opposite. We can make current flow either way through these loops. So, okay, great. Things we can do with two diodes. That's okay. We've had a good review of Kirchhoff's voltage law, which we're really going to use as we start working with these transistors more. But we haven't explained at this point with these two diode models how we would get current gain and why this device would work any differently than just the two diodes, which doesn't really do much for us. Doesn't show how we get any kind of gain. Well, as it turns out, at this point we've got to get rid of just our back-to-back diode model and dig back into this very important thin, lightly doped layer concept. And this is where our bipolar junction transistor under proper biasing is going to depart from just regular diode and PN junction reverse forward biasing. Okay, to do this we're gonna zoom in again, and for those of you who are reading the notes, I'm using kind of a color coding of importance. We start out with good things to know in the green, things that are getting more essential to a figure or a developing topic in yellow, and even more important in orange, and then red is the real crux, key to how the whole thing works, or an important safety point in working with devices. So as you go through this chapter, be sure to use the color coding to help guide you through the steps of how things work. We are going to go ahead and step through that though right here and try to zoom in a little bit. So we're going to actually step through the journey of an electron. So we've got a dotted line showing our charge flow, not a solid, because we are now departing from conventional current standards. So we're showing an electron flow. So we're going to come out of the back end of the battery at the emitter. Electrons are going to flow through our limiting resistor, so we don't get too many going at once. And electrons are negatively charged. They're going to hit the heavily N-doped material of the emitter. And you can think of those electrons as kind of repelling, like repels like, in terms of electrostatics. So the majority charge carriers in the N material, there's plenty of them, lots of mobility. They're going to go scooting across the emitter very easily, very few ohmic losses, and they're going to hit this forward bias junction. I mean, they still are going to need some energy to climb up that fixed charge hill, but they're getting plenty of it from our biasing source. We're giving this way more than, say, that 0.7 volts we would need to get across it. Okay, so if this were a diode, having allowed those electrons to climb the energy hill across this interface, they'd hit the P material, and in a diode there'd be a lot of charge carriers in the P, a lot of holes pre-existing here. And those electrons would combine with the holes and complete the circuit, and we would effectively have positive charge flowing into the P, which is represented by electron flow coming out with a base current. But that's not what happens in a bipolar junction transistor. Rather than recombining with the majority charge carrier holes in the P, remember that P layer is super thin, and there's not a lot of holes there. We didn't give it much of that trivalent dopant. So what actually ends up happening is the electrons that are coming across the junction that we've pushed up the energy hill, they just continue through. Maybe a few get recombined, but 10% max, more like 1 to 5 according to our textbook, you'll see down in the paragraph below. Then they make it across and they're going to hit the PN junction base to collector. Now, if we were conventional current, we'd be looking at this and going, I can't get across this. This is reversed biased. But we're electrons. We're pushing an electron across this. So electrons are going to get to this interface, and they're going to see what's effectively here in this region. They get across the interface, and they're going to see effectively a zone depleted in the charge that they're carrying, this net positive charge. So this portion of the collector really wanted to have some electrons, and it doesn't because it recombined with some of those intrinsic holes in the base. It's perfectly happy to get some electrons coming scooting across the base. So what actually happens is the electrons that we originally pushed out of the negative end of our battery came across the emitter. We pushed up the hill emitter base. They scooted across the base without getting recombined or flowing back out, and they got accelerated. They flowed down gradient into the collector, and then of course are accelerated across the collector because it's attached to the positive terminal over here. So if we look at an energy hill, we can do the same thing, and we'll look at the conduction band mostly because we're doing this in terms of electrons. Electrons need to be pushed up the up gradient. Holes need to be pushed down. Holes fall up, electrons fall down. So we start over here at the lead attached to our emitter. We can flow through the emitter. We have our emitter bias voltage, our VEE. It pushes an electron up. We'll even do this with a marker. We've got an electron flowing. It gets pushed up gradient with VEE. It scoots across the base, doesn't get recombined, and now the base collector PN junction is oriented the other way such that it accelerates, it sucks the electrons down into the conduction band. So it's actually like a little battery going the correct way to make those electrons have more energy, and the electrons flow back out and into the rest of the circuit. We could make the same argument from the standpoint of a hole. Holes fall up, and have to be accelerated down. So of course we can look at our charge flow from either standpoint, but we've done it in terms of electron flow. So that is the main way in which our bipolar junction transistor is going to differ from just two diodes. We have charge flowing between the emitter and the collector because the charge doesn't recombine in the base the way it normally would for current flowing just through one loop of a diode. And at this point we're going to depart from the materials science, and we're not going to really close that loop of exactly how that charge flow relates to the current gain. It is, we'll just state it without necessarily explaining it. But the fact that we have charge coming from the emitter to the collector not getting recombined in the base means that any charge we inject into the base helps the journey of charge going across. So the base current, whichever direction it's flowing, and it can really only flow, conventional current can only flow this way, electrons are flowing in that direction, but the more charge we put in the base in the correct direction, the more we enable charge to flow across the device. We make it easier for these electrons going across, or positive charge going the other way, to make it across. So you can think of the base current as facilitating the electrons that are crossing this thin region and making it easier for them to get across. So current entering the base is going to make it easier for current to flow emitter to collector. And that's how we get the current gain in the device. The more we put into the base, the more the device can transmit emitter to collector. And that's why we consider a bipolar junction transistor to be a current gain device, not a voltage gain. But of course, by Ohm's law, we can get a voltage gain if we have more current. My gosh, we have a resistor. I bet if we have more current flowing through it, we'll have a bigger voltage drop over it, and voila, we have a voltage gain. So of course one relates to the other. Okay. So at this point we understand a little bit about the material science of how a bipolar junction transistor differs from a diode. It's got 2p-n junctions just like a diode, but because you got that thin, very lightly doped base, it's going to work differently from the standpoint of charge that's transiting the device emitter to collector, which is really our main circuit. We've stated the relationship between charge flowing into the base and the ability to get charge across the device emitter to collector. Okay, now we're going to step back from that mechanism a little bit. We're not going to go back into the polarization of the junctions so much. We'll revisit it really briefly when we look at lead identification, but from here on out we're going to use mathematical representations of those ideas, and we're going to talk in terms of the spec parameters of the device and just use those in a circuit. We're electronics technicians in training here. We're not training to be semiconductor designers necessarily. We're just going to use their products. So we're going to discuss bipolar junction and later on field effect transistors in terms of what they can do in terms of gain, the impedance they have, and the departures from ideality. So that is a little bit easier for us. So there's some important rules that we can gather based on a bipolar junction transistor's operation, and the first one is return to good old Kirchhoff's current law. Let's go back up to our schematic here, and this is an application that's super important for how we use these devices. If we were to, I'm going to go back to conventional current now. If I have conventional current that flows in this direction, and we have some more flowing here, this is my I collector. If I have electrons flowing out of the base, I have conventional current flowing in, charge for charge, there's my base current, and given the orientation of my emitter source, I have an emitter current. So given that there's no current jumping out of the side of the transistor or arcing out of our leads, certainly, we can state some relationships about all of these different currents, and namely that they all add up. So we can sum the current coming into the base and in through the collector is going to equal the current flowing out of the emitter in this configuration. So we're going to use that. We've stated that here. We're going to use that relationship in the future when we analyze how transistors work and how they give us our current gain. And so there's rule number one. So here's rule number two. There's not a lot of base current. Remember, base current's the controller. So we have little bits of current going in the base and controlling big currents flowing through here. So base current's going to be orders of magnitude less than collector and emitter currents. Generally speaking, it's the signal. So typically collector and emitter currents are bigger, way bigger. So we can make some approximations and say if the base current's pretty small, then, you know, to approximation, collector and emitter currents are kind of equal. And if they're not, you know, you can run through the math and probably see that things, you know, cancel out when you lop off a few decimal places. Here's another big important thing. When this is running, generally speaking, this interface is the one that's forward biased. If we have a PN junction that's forward biased and we knew the type of material, we know what that energy hill is. We know what this one is. The base emitter junction energy hill is our forward bias. So if we've got our transistor on, V forward, we know what that energy hill is between the base and the emitter. It's important to remember we have no stinking clue what this one is. The size of this really big hill, we don't know what it is. We always have to get this from inference by difference from looking at other things in the circuit. We get this from Kirchhoff's voltage law for the rest of the circuit. But we know the base to emitter junction. If it's open, if it allows current to flow, we know we have supplied the forward bias voltage. And again, that's going to be 0.7 if it's silicon, maybe 0.3 if it's germanium. Whatever it is, it's going to be that known characteristic of a semiconductor. And for this class, that's pretty much always going to be 0.7. So there's something we know. We got Kirchhoff's current law. We can approximate the base is small, so we can relate current and emitter currents, collector and emitter currents to one another. They're almost the same. And we know the voltage at one of those PN junctions. We know the base collector junction's reverse bias. We have no idea what it is, but it's pretty big, and that's where we get a lot of our gain. Generally unknown. So we're not going to be tempted to think of what it is. We're just going to solve it by difference. And in fact, what we're going to solve generally by difference is the voltage drop all the way across the device. We're going to get the collector emitter when we look at these in circuits. VCE is what we're going to solve for. So we're going to end up having two loops. The big loop we're controlling, and the little loop that's our signal. Okay. And conventional current flow. Conventional current's a positive charge, so we can think about positive charge flowing into the p-type material and out the n-type. So conventional current is going to flow into the collector and base and out the emitter. For an NPN, it's going to be the opposite for a PNP. So we do have to remember our rules about polarity there. Okay, that is it for this lecture. In our next one, we're going to define our beta and alpha. which are our gain parameters for the transistor. These are inherent to the transistor and pretty much why we use them in circuits. So this is where we take advantage of those crazy PN junctions and our thin, lightly doped base and all of those semiconductor properties. We're going to encapsulate all that lovely material science into two performance parameters called the current gain parameters, and then we're just going to use them in circuits and have fun with them. We'll say thank you to the material scientists that gave us these nice transistors, and then we're just going to use these spec parameters and use them in circuits. We will refer back to the material science basically to make sure we can identify leads and polarities for PNP and NPN devices and make sure we hook them up properly in our circuits and not backwards. But beyond that, we'll be using the spec parameters. So stay tuned for alpha and beta current gain.